now that you've kind of gotten your hands dirty on the chi-square test and we kind of understand it, we know that most of what we do, it's so complicated, it'll just be technology calculating things for us. As long as we know how to calculate degrees of freedom. Now this last page, we'll make a comment about the effect of sample size on chi-square. In the example with the gender, we had 1,500 college students. That was quite a big sample, but what if we have a smaller sample than that, quite a big sample, even bigger than that? How would that affect things? With other hypothesis tests, we have seen that sample size can affect the p-value and our conclusion. This is also true for chi-square. To illustrate this idea, we multiplied all the counts in the Oklahoma gender and driving after drinking data by 3. The original data was here. It was, have you drank alcohol in the last 2 hours, males in this row, females in the second row, and then the totals, male and female, together in the third row. And then the columns are yes, no, and then the totals. Males and females that said yes and no, or sorry, males that said yes, males that said no, total here. Males that said, or females that said yes, females that said no, total here. And then male and female, all the students that said yes, all the students that said no, and then the total here, total number of people. Let's multiply all those numbers by 3, for example, like it said. We have, instead of about 600 people that we polled here, the total number of people, now we have 3 times that many, 1,800 or a little more. Just to kind of imagine if the results were the same kind of proportion-wise, the number of males out of the total number is the same, and all the yeses and nos were about the same proportion, but we had, say, just to make it interesting, we have 3 times as many people that we're looking at. Now we'll examine what impact this had on the expected count. So first, let's look at the conditional percentages. So kind of like we mentioned, this table represents the original data, same amounts, but now instead of just listing the number of males, for example, who said, yes, I did have alcohol in the last 2 hours, 77, now I'm saying it's out of the total number of males, like we saw with the gender example on previous pages, gender and body image. And then the percentage beneath it. So 16% of males said they had to drink in the last 2 hours. 11.6% of females said they had. 84.0% of males said that they had not had alcohol in the last 2 hours, and 88.4% of females said they had not. So we have the percentages, but notice when we look at this one where it's multiplied, all the values are multiplied by 3. The number of males who said yes multiplied by 3. The number of females who said yes multiplied by 3. The total number that said yes multiplied by 3. Everything's multiplied by 3. So it's pretty much, imagine if we had pretty much the same results proportion-wise, but we polled 3 times the number of people. Notice that the percentages stay the same. Proportions are preserved here. So still 16% of males said that they had a drink in the last 2 hours. 11.6% of females still. 84% of males said no, they hadn't. 84% still, even though now there's 3 times as many. And then 88.4% of females said they had not had one. Still the same, even though we have 4 times as many females, and so on and so forth. So notice that the conditional percentages do not change. So the new data, quote unquote, we didn't really collect this data. We're just imagining it, multiplying everything by 3, and just to see what would happen if we had a bigger sample size. It shows the same relationship between gender and drinking before driving. We use technology to find the expected counts on the chi-square test statistic for the original data, and the data multiplied by 3. So here are our results. We do all this with technology, of course. Let's see. So the original data, before I multiplied by 3, this is our expected counts, okay? Because we expect the same, whatever this percentage is, 93 out of 526. Oh, sorry, 93 out of 619 is whatever percentage, some percent. We expect that's the percent that will say, yes, I have had a drink for the total number of people. So we expect that's a percent to be the same here and here, kind of. Anyway, we put that data in, and the chi-square test statistic and the p-value is brought in here as well. So we got a p-value of 0.2, about 0.2008. That's for the original data. So now, like we said, all the proportions are preserved, the percentages are preserved. So that shouldn't change it. It's just the sample size is kind of what's changing here. Now we multiplied the data by 3, and we got quite a different p-value. The chi-square test statistic was 1.6 for the original data with 3 times as many people, 3 times the sample size, I guess, is what we're talking about here, because it might not be people in all examples, but whatever the sample is, it's going to be people, whatever the sample size. It looks like the chi-square test statistic is now, instead of 1.6, it's 4.9, so it's grown quite a bit. And the p-value here used to be 0.2 about. I'll put wiggly equal sign because it's not exactly. And then here now it's 0.02 and then on and on. I mean, 0.026, I should say. So notice that by multiplying the observed count by 3, it also triples the expected count and the chi-square value. So because it went from 1.6 to 4.9, that's about 1.6 times 3. This increase in the chi-square value from 1.6 to 4.9 gives a statistically significant p-value now of 0.0267 from the original 0.2008, which changes our conclusion. With this larger sample, the evidence is strong enough to reject the null hypothesis. We conclude that the gender is associated with drinking alcohol before driving. Let's see, we'll scroll down to read the rest here. Okay. The variables are dependent for drivers under the age of 21 in Oklahoma. With this sample size, the data provides evidence in support of the Oklahoma law that forbids sale of 3.2% beer to males and permits it to females with the goal of improving traffic safety. What's the point? We see once again that sample size affects the p-value in a hypothesis test. This means that a small sample may not detect a relationship that exists between two categorical variables in a population. Conversely, a large sample may indicate that a relationship is statistically significant on the basis of differences in observed and expected counts that are actually not important in a practical sense.